fundamental group of a circle is isomorphic group of integers, and so informally, an integer corresponding to the loop is a number of kind of full turns you do when you follow this loop around the circle. Counted with signs, and then we showed that this can be used, for example, to prove relatively easily two peculiar theorems. One of them is Brouwer fixed point theorem, which tells that if there is a continuous map from a disk to itself, then there is necessarily exists a point which is invariant under this map. And we also showed Borsuk-Ulam theorem, which so now in this setting we have some two-dimensional sphere, and you can see that it's mapped to R2, and then the statement was that there necessarily exists a pair of antipodal points which have the same value. And then we showed that the fundamental group of a product of topological spaces equipped with product topology is, well, assuming they are path connected, is isomorphic to a product of the corresponding fundamental groups. Maybe it's instructive to give an example for this, for the use of the statement. For example, for phi1 of T2, we know that T2, a two-dimensional torus, is consists of a product of two circles. One is a kind of meridian circle, and the other is so one is longitude, and the other is kind of meridian circle. And so from this statement, we know that it's isomorphic to pair to the product of fundamental group. So circle and another copy of it. And each of them we show the isomorphic to Z, so this product is isomorphic to Z square. How this can be understood? So you're probably already familiar that the torus, for example, can be understood as a quotient of a triangle where we identify horizontal edges and vertical edges. And so the homotopy, the statement is that the homotopy classes of loops are in one-to-one correspondence with a pair of integers. And so again, formally, this is one integer is how many times you wind along one circle, meridian here, and the other integer is how many times you wind longitude. So, for example, if you have something, it's hard to draw here, but if you have something which goes once around this direction and twice around this direction, this will give you a pair of integers 1. Okay. Of course, this is a closed loop because this point is equal to this point, and this point is equal. Any questions about the last lecture? Not. So, okay, let me continue with the following definition. Now we want to kind of study, again, various properties of the fundamental group, which in particular will help us to calculate it for other topological spaces. So one is very important property is well, kind of there will be a collection of properties related to the following definition of push forward. So consider, which kind of gives us this will allow us to compare a fundamental group on two different topological spaces. Suppose we have some map phi between a pair of topological spaces, and okay, we fix a base point here x0 and some base point y0 here, which is an image of this base point under our map phi. And then we define push forward, what is called a push forward of the push forward of a map phi, which will be denoted by phi with a star as an index, and it will be a map between the corresponding fundamental groups. Here I can see the base point, some fixed point x0, and here my base point is given by the image of x0 on this map phi, and this map is defined as follows. So here, again, the elements here are represented by some loops in X, topological space X, which are some maps from a unit interval to this X. Again, we also have a condition that f of 0 is the same as f of 1, so it's a closed loop. And what we can do, we can compose this map with map phi to get a loop from an interval. Sorry, to get a map from an interval to y, which also will be a loop because the f of 0 was the same as f of 1, so the composition will also have this property. Then we just send this map, this class represented by f, to a class represented by the composition. So that's why you can send this. So this phi kind of pushes the map phi, the map f to the map valued in y. That's why it's kind of called push forward. Sometimes it's also can be called or induced homomorphism. So this name is justified because this map is actually a homomorphism. It's not just a map between these sets, but it's a map, considered as a map between groups. It's a homomorphism, and principle one has to argue that this is indeed the case. But first, we also have to argue that, as usual, we have to argue that the map is well defined, so the result is independent on the choice of representative. So as usual, just take another, suppose another loop f prime, which is homotopic to f using some path homotopy capital F. But then it will immediately follow that the compositions will be also homotopic just by using a composition of path homotopy F with our map phi. So if we deform, informally, if we deform this loop F in X, some loop here, somehow this if you compose this deformation with phi, this continuous deformation in y. And this means that phi star applied to f, phi star calculated using the representative f is the same as phi star which we have using representative f prime. So this is indeed well defined. And then we also want to check that this is indeed homomorphism. So we need to check that it respects the group operation. So for this, let's consider a pair of loops in X. And consider their product in the fundamental group of X. By definition of the product in pi 1 of X, this is a class of a composition of loops F and G. And so this is just definition of product in pi 1. And then we apply to it our push forward. By definition, sends this to a composition of phi. So this is a composition as a composition of functions, and here this is a composition as a composition of loops, which are kind of concatenation. They're concatenation. And but of course this is distributive, so you can instead compose f with phi. This will give us some loop in X, and then compose it with composition of phi. Again, this is a composition of functions in the usual sense, and this is a composition of loops as a kind of stacking together. And then we can use the definition again, the definition of pi 1, definition of the group operation in pi 1 of y to see that this is the same as the class of phi composed with f multiplied by the class of phi composed with g. And then we use the definition of, again, use the definition of our push forward phi star. This is the same as phi star applied to the class of f multiplied to phi star applied. This proves that well-definedness of this map on pi 1s. And this proves that it's indeed a homomorphism. Any questions? So the push forward has some nice properties. First property is that if so let's take identity map, just a map from X to itself with identity, and then its push forward is identity homomorphism on the corresponding fundamental group. well, this is a kind of trivial statement. It's immediately seen by the definition. And the second property is also almost obvious, but still kind of non-trivial. So if you consider, consider a triple, now a triple of topological spaces x, y, and z, and consider a map phi from x to y, and the map, let's say, psi from y to z, and then we can consider their composition, psi composed with phi, which goes directly from x to z. And we also will consider some base point, x0 in x, and correspondingly the base point y0 in y, so that y0 is the image of x0 under the map phi, and similarly consider base point z0 in a topological space z, which is an image of y0 map psi. And then the statement which we want to make is that the push forward of the composition is equal to the composition of push forwards. So this is a map which goes directly from phi 1 of x to, well, let me write it here. Consider phi 1 of x, x0, phi 1 of y, y0, and phi 1 of z, z0. So here we have psi star, phi star, psi star, and or we can go directly using the psi star composed with phi star. And the statement that this diagram is commutative, so you can go either like this or like this, and you get the same. And why is this? Well, again, this is kind of obvious. So we want to consider, we start with the loop in x, so we consider so we consider some element here in pi 1 of x represented by some loop f, and then we can compose it with phi to get phi composed with f, and this will give us a representative of the action of the push forward, which is valued in this pi 1 of y, and then we can compose this thing with psi, which correspond to the action of the push forward of psi here. But this is the same as this composition can be done in a different order. This is just the usual composition of functions. So we can first compose psi and phi, and then compose it with f. But this would correspond to the action of the sorry, here actually I wanted to write this. Yeah. Otherwise it would be tautological. And this gives us a representative of the action of push forward of the composition on f, on the class represented by f here. So this is the same because we can change the order of compositions. We showed that the left-hand side and the right-hand side give us the same result if we acted on a class represented by f. And So for those, let me make the following remark. If you're familiar with category theory, these statements can be understood as the following fact, that pi1 is a functor from a category the category of, well, to be precise, this will be pointed topological spaces to the category of groups. Here in this in the first functor, so you can write something top. Well, star meaning this is a pointed topological spaces to pi1. So this is a category of which objects are topological spaces with some selected point inside it, and the morphisms are continuous functions between them, which send the marked point in one topological space to the marked point in the other topological space. And here the objects are groups and the morphisms are homomorphisms. Anyway, this is not, we are not going to use this, but yeah, this, if you're familiar with category theory, this may give you some sort of a bigger picture. In principle, you can also kind of make this statement more refined. So this is actually, as a functor, is also not just, you can consider both categories as category with products, because and this will be still a functor on this kind of functor on this categories with additional structure, because it behaves nicely under multiplication. So now we want to formulate some proposition which, again, will allow us to compare fundamental groups at different topological spaces. Well, this will be some very particular case. Suppose we have a map R from X to its subspace, which is a retraction. Then the corresponding, so let I will be corresponding the canonical inclusion map from A to X. Then the statement that the push forward, which will be a map from, let me fix, yeah, let me fix a base point in x0, so it can be both considered as base point in A and in X, since A is a subspace in X. And then this is can be understood as a map from, sorry, as a homomorphism from pi1 of A x0 to pi1 x 0. Yeah, I'm kind of abusing notation. I mean, here this x0 is a point in A, but of course it also can be also a point in X since A is a subspace. Okay, the statement is that if R was a retraction, then this inclusion map is injective. And the second part of the statement, if A is what is called is a strong deformation retract, X well, I will tell you when we profile, I will tell you what this strong means. Then this thing is an isomorphism. Well, in principle, this statement is true without this assumption of strong, but and we actually will prove. I mean, it will follow from a more general statement later. But to make things simple, I will assume this strong condition, which I tell you in a moment. But this, I mean, there actually in some definition of deformation retraction, this assumption is they actually define, so it's actually strong deformation. Well, maybe I should let me say it now. So the strong deformation attack meaning there exists a homotopy F X is a homotopy F, which is a map from, as usual, is a map from X times interval to X, such that. So far, I'm just repeating the definition of the deformation retraction as I define it. Then F, so that F restricted to 0, meaning the second argument is restricted to 0. It's identity on X, and F restricted to 1 is a composition of inclusion in R. So this was in the usual definition of differential retract, we just defined that there exists a homotopy between this composition of retraction with inclusion and identity on X, but with a strong condition. We also want that if I take an arbitrary t in this interval, then this and so restricted on t and also restricted on, well, let me write this way. So restricted on arbitrary t, and I restrict it to A, the subspace A. Write it large. Restricted F restricted to A times t. So I take arbitrary value t here, and I restrict it to a subspace A here. This should be identity on A for any t. The additional condition of this means. Again, in some places, like Hatcher book, for example, they actually define just deformation retract using this condition. But as I defined before, it didn't have this, but for simplicity here, I will assume this condition. maybe I also should recall the definition of the usual retraction. Retraction such that we require that R restricted to A is identity on A. Okay. Which okay. So now let us prove this. First, let us prove the first half of the statement. Okay, so again, this condition of retraction can be clearly written as follows: as the position of R with inclusion is identity. Okay, so because restriction is, taking the restriction is the same as just taking a composition with the inclusion map. And then we can apply push forward to both sides of this equation and use the property that it's the composition of the push forward of the composition is the composition of push forward. So we get that R star composed with I A star, and here we know that the push forward of the identity is identity, which is a map, identity homomorphism on pi 1 of A. Well, let me keep this point x0 completeness. And of course, we know that this is this has identity has trivial kernel. And this follows that this homomorphism should also have a trivial kernel, which means that this is injective. So this was easy. And, for the second part, okay, so we use the existence of such f here, as I just wrote, and we take any loop f in X, and we compose it with this homotopy capital F. So we compose it with F. And particularly if you consider the restriction of F on 0 applied to F, this is the same, since we know that F is the restriction or to 0 is identity, this is the same as F. And this is, we know that this is homotopic. This is a path homotopic to restriction of F to 1 composed with F, just using as a homotopy, we use the composition of the full F of this full function capital F with our path F. So we use it as a path homotopy. And now we use the fact that the restriction of F to 1 is this composition of our retraction and inclusion is F. And we can kind of change the order of the composition and obtain that this is a composition of inclusion map with something here, and something here can be understood as a path. So this instance is a composition of F with retraction, which maps, which takes us from X to A. So this can be understood as a loop in A. So what we showed is that if you take any loop in X, it's path homotopic to a composition of some loop in A with inclusion map. Now you can consider, so we have a path homotopy relation between a pair of paths, which are actually loops in X, and then we consider the corresponding classes, and for classes this equivalence will just become equality. So this means that the class of F is equal to the class this guy is an element in pi 1 x0, but this is by definition of the push forward. This is the value of the push forward of the inclusion on composition R is F, which this thing is an element of pi 1 x0. And so what you show is that for any, so since F was arbitrary for any element of the group pi 1, there exists an element of pi 1 of A, so that this push forward of the inclusion gives us back this element. So this shows that indeed this is injective. And we already know that it's from the previous part that it's it's rejective. Rejective, because we obtain that any element is in the image of something. Any element is the image of some element in pi 1. And before we already showed that this is injective. This was true for any retract, and if you combine this, we get that indeed that this is another isomorphism.
Professor.
Yes, there is a question.
Yes, I don't understand where the assumption of strong deformation retraction is used, and is it not true in general for general deformation retraction?
It is true. Well, it's true that we will show that for general homotopy equivalence, this is push forward of homotopy equivalence is isomorphism. We actually will show it shortly. Yeah, this here we use that this is strong because we wanted this to be a path homotopy. So we want this to preserve the base point. So we used, I mean, it still would be true that this is homotopy, but we couldn't just use, I mean, one can in principle deal with this thing, but for simplicity, if you we assume if you assume this is strong, this is just the base point will be preserved. So this will be actually path homotopy, not an arbitrary homotopy, and not just a homotopy between maps. Okay. You want that this for any t, you want that in particular this is of f of x. Of this of x0. You want this to be which is f of 0, f of 1. You want this to remain x0 in particular. Again, shortly, we showed that any deformation retract is a homotopy equivalence, and we will show shortly that actually for any homotopy equivalence, the push forward is an isomorphism. But you will see we will have to be more careful how this treating the base point. Here we can be kind of cavalier about the base point because it just stays, it doesn't move anywhere. Any other questions? Yeah, so we're going to prove the following proposition, which I just mentioned, that if we have a map from x to y, which is a homotopy equivalence, meaning it has a homotopy inverse, then the corresponding push forward is an isomorphism. Is related to what I was kind of mentioning in the very beginning of the course, that this algebraic topology deals with kind of invariants, algebraic invariants of topological spaces, meaning for some topological spaces, let's say it's some kind of algebraic structure. These invariants are usually invariants, so they kind of invariant, meaning they're the same, not just they're necessarily the same for homomorphic spaces, but it's actually invariant under kind of weaker equivalence relation, being homotopy equivalence. So the algebraic objects which you get associated to the topological spaces, they depend only, they're the same for not just for homomorphic spaces, but for homotopy equivalent spaces, where you can allow more kind of informally you allow more deformations. And kind of, as we've seen, you can kind of shrink some parts of your topological space. for example, point is point and disk are the same, up to homotopy equivalence. But you still kind of preserve some information about some sort of non-trivial loops and some sort of non-trivial cycles more in general, like holes, something like holes in the space. This you cannot get rid of. Anyway, to prove this, we will first consider the following lemma. So proof a bit later. Once we prove this lemma, it will be rather easy. Okay, so what's happening here is the following. So here we have consider homotopy between maps from X to Y. Which is so it's a homotopy between Phi0, which is of course, I mean, using our usual notation is the same as phi restricted to 0 here, and phi1, which is phi restricted to 1, and also consider so we can consider then the following path H in Y, which is defined as follows. I take some argument S here. The corresponding function gives us the value of this phi at x0, comma s. We can yeah, I guess I can draw it. Well, let me draw it here. So how do you see this? We have some x, space x, have some space y, have kind of phi, instead phi restricted to t. So there's some family of maps parameterized by an interval from x to y, and you consider a point x0 here, and for this point, if I wear my t here as this kind of point moves around from phi 0 of x0 to phi 1 x0. So this is this image of my base point x0 in x. It once I change my homotopy parameter t, it moves in y, and this gives me some path in y, which I denote as h. Okay, and okay, this was kind of assumptions of the lemma, and then the statement that the following diagram is commutative. So you can see the pi1 of x0, and then we can consider the push forward of phi 0 this will be, well, by definition of push forward, this will be mapped into, sorry, phi 1 of y is base point phi 0 of x0. And you also can consider the push forward of f1, the final map which we have in this family, which can be valued in phi 1 for gain y, but with base point being phi 1 of x0. You also can consider a third map. So we consider it, we know that if you have a map, sorry, if you have a path connecting two different base points, it induces, we can construct a corresponding isomorphism between the fundamental groups associated to these two different base points here. And this is what we denoted as beta beta h, right? Because h is a path which starts, by construction, h is a path which starts at phi 0 x0 and ends phi 1 of x0. Statement that this diagram is commutative, meaning that you can, well, meaning that this map is a composition of these maps, or if you wish, in just phi 1 star is the same as beta h. Just this statement. Statement which we want to prove. And well, the proof is done more or less directly. So consider, maybe I should draw this picture again. Consider some, so we have x. We consider family of maps to y. X0, this is, let's say, phi 0, 0, this is somewhere else, phi 1, 0, we have a path, this is our path h between them. And okay, what we do, we just apply the this both sides of this equality, which we know to show, to an arbitrary element. So we consider, first consider phi 1 phi phi1 star applied to F, which is so consider some F. Consider arbitrary loop F in X. This gives us some element in phi1 X 0. Should look something like this. By definition, this is just a class of a composition of phi1 F, which is so just take this loop composed with phi1 and get some sort of some loop here. Okay, and then, and if you consider the right-hand side of the equality we want to prove and apply it to arbitrary element represented by F, we have, we want to apply this composition to the class of the same element. And this is by definition, so if you remember, so okay, let me do it in steps. So this is BH. First applies the push forward of phi1, and this is just taking a class of the composition. And then we apply BH, and if you remember, the definition of this BH is that we essentially need to take this. So we have a, so this is our phi0 composed with F, and we want to then, so what we want to do, we want to get an element, we're going to get a loop at this base, sorry, we want to get the
Professor, shouldn't it be phi subscript 0?
Yeah, sorry, yeah, I'm trying. Sorry, yeah, here, okay, here we have phi0, yes, thank you. Phi0, and here we have phi. So we consider this, thanks. So our question, our goal is to show that this is the same for any F. So we need to, so this thing is phi1 of y with base point phi1 0, and this thing is a loop at x0. So we need to transport it here using the path h. And, so to do so, we first so we can first apply h bar. So we go here, then we follow our loop. And then we go back using h. So this takes us, this makes that this from a loop based at this point, we make a loop based at this point using our path h. So again, this is just a reminder of the definition of this homomorphism beta h, which is actually, which as we showed, it was actually an isomorphism. Okay, so what we want to show, we want to show equality of these things. So it's sufficient to show that these are they're path homotopic. So we want to show that this is this path here is homotopic to this composition. And we can do this by presenting an explicit path homotopy capital F. And this capital F, as usual, so it's a path homotopy, so it's a map from a product of intervals to Y, and we take it so that so consider again T to be our homotopy parameter, which we buy. So this is the first argument is a parameter along the path, and this is a homotopy parameter T. So for so we take F such that the restriction of F to a particular value T here should be a certain path will be given by the following composition, where HT is a certain path, which I will define in a moment. Here we take restriction of phi to a particular T, meaning we take a fixed value of the argument here, composing it with F, and then we compose it with the path HT bar, where what is HT bar? So we want this to be a homotopy which relates this loop and the loop obtained by going first here, here, and taking it here. And what we can do, so to kind of to deform one to each other, we can just start deforming this. Use our homotopy between maps from X and Y to move together this loop here, and also move this base point. So we can consider where the base point is mapped at an arbitrary value of T, so this will be F restricted of T of X0, and it moves from 0 to here when we change T from 0 to 1. And so what we can do, we can consider kind of intermediate position and define here for this intermediate position of base points the path HT, which goes from this base point at arbitrary T to this one. And more explicitly, if you want, this is just define this HT by a function, you just use the following. So HT of S is H. It just goes along a part of a path H. So we can just use H, this function H, to define this its piece here, just by doing some rescaling. It's S times 1 minus T plus T. So you can see that when T equals, okay, first for when S equals 0, this is the value H of T, which is indeed this point. And when S equals 1, this is the same as H of 1, so it's the same as this point. And also when, if I take T equals 0, this becomes the full H as we want when T equals 0. And when it's T equals 1, when I take T equals 1, so here we have 0 and we have just H in 1. So this becomes constant at S. So this is a path which just stays at this point. And this is okay, so this defines as HT and HT bar, and this is here in the middle. This is just this is an image of this loop f again at arbitrary t. So this is a composition of f phi at arbitrary t with f. So again, geometrically you just deform. This gives you a deformation of this loop, which goes like this to a loop which goes like this by deforming, kind of moving this point and deforming this loop accordingly. Okay, so so this gives us the path homotopy. So this shows that these are path homotopic, and then therefore these two elements are the same. Any questions? Okay, now we are ready to prove this proposition. Position star. The push forward of homotopy equivalence is an isomorphism. So we have phi, and assumptions we have phi, which is a homotopy equivalence. And so by definition, there exists a map psi in the opposite direction, y to x, which is a homotopy inverse, meaning that if you take a composition of psi with phi, this is homotopic to identity on y, and the composition in the other way is homotopic to identity on x. Okay. And so let's see what happens if you consider the corresponding push forwards. So let us start with, let us fix again some base point x0 in x, and then consider this fundamental group, and then push forward phi. It will be a homomorphism to pi 1 of y, with base point being phi of x0. And then let's apply to this, we apply push forward of psi. This will get us to the back to pi 1 of x. However, the base point will be different, because in general, the base point we obtain by evaluating psi on this. So the base point will be psi of phi of x0. So we don't don't actually get to the same. Exactly to the same group. We get to the fundamental group, but with a different base point. Okay, and well, let's see what happened, and let's us do this again. Let's apply. So to this, we can again apply push forward of phi. Which will take us to the fundamental group y, with base point, which is phi of psi of phi of x0 this. Okay, this will be enough for us. Well, you can see kind of, okay, I use the same notation phi star here and here, but, well, to be kind of careful, they act between kind of different fundamental groups. The fundamental group defined for different base points. So let me, and to distinguish these two maps, let me put a prime here. Okay, now we can use our lemma. To show the following. Okay, so suppose so we know, okay, let's consider this. Let's consider this equivalent. So this homotopy, statement about homotopy between a pair of maps, and since we know that this is so this erased, yeah, this is homotopic to this, and we showed that if there exists a homotopy between a pair of functions, they differ by beta h, which is an isomorphism. Right? So this means that using lemma, this means that this composition is well, let me write it kind of like this: is identity. This composition of the corresponding push forwards is identity on phi 1 of y up to an isomorphism. But we know that the right-hand side, so meaning that there will actually be identity because you have to include this beta, meaning that there's actually you have to take a composition with the isomorphism given by this beta. But this is enough for us. So this means that since identity itself is an isomorphism, this means that this composition is an isomorphism. Isomorphism you can always invert. The composition of isomorphisms is an isomorphism. Okay. And in particular, this means that so we consider composition. Actually, let's see if I took psi and phi. So actually I want to consider this phi star here. It's, phi star which acts between this and this. So let me take this thing. And this implies, so if this is isomorphism, this means particulate has trivial kernel. It's injective. If it has a trivial kernel, then this map which you use first should also have a trivial kernel. And this means that psi star should be injective. Okay. And now let us consider the second relation. And for this, let us consider a pair of push forwards here and here. So again, from the lemma, we know that these maps are homotopic. This means that their push forwards are the same up to an isomorphism, meaning that, again, that psi star composed with phi star is identity on phi 1 of x up to an isomorphism. Meaning, again, this is just equal to this composed with some isomorphism given by this some beta for some h. This is an explicit choice of this h is not important for us. It's only important that that BH is an isomorphism. And then similarly, you can say, okay, if this is identity up to an isomorphism, this isomorphism identity the cell is well, this means that this is isomorphism trivially, and and this means that in particular, so since any isomorphism is a surjective, this means that the map which we apply second here must be surjective, because its image should be the whole group. It means that psi star is surjective. So okay, this shows that this psi star is both injective and surjective. And this means that it's an isomorphism. Because homomorphism, which is both injective and surjective, is an isomorphism. Any questions? Then again, from this statement, actually, it follows that any deformational tract, which we showed that is a homotopy equivalence, is actually is an isomorphism. But as you've seen, here we have to kind of we have to be careful. The proof is a bit tricky. Like it's not completely straightforward. You have to be careful what is happening with this base point. Okay, so our next goal, and this will be more or less the final thing which we will do before we turn to study homology theory, is to prove Van Kampen's theorem and to show how one can use it in some examples. And okay, so before proving Van Kampen's theorem, which will be quite a bit tedious, we will need to show the following lemma, which is kind of already will give us a partial proof to the Van Kampen's theorem. I guess I will formulate it, but I will probably not going to be able to finish the proof today. So suppose our topological space is powered by a collection of open sets the alpha such that we usually have some base point in X, and we want this base point to belong to all of them. Oh, sorry. Yeah, well, the same. Okay, you can choose. Yeah, there is a point which exists, a point which belongs to all of them, and we will choose it to be our base point. And we also want the following conditions, that A alpha are is path connected, and actually for any alpha, and also all pairwise intersections are path connected for any alpha and beta. For example, if you want, when they kind of schematically, okay, you have a bunch of A's which cover everything, and they contain some common point, and you also want the all intersection to be path connected. In particular, you cannot allow, if you imagine this on a play, on some sort of space on play, you're not allowed to have something like this, right? A pair, not allowed. Have intersection. Again, this is just a schematic. This is we are working on some abstract topological spaces. Some subspaces of R2. Anyway, and there's a statement that for any loop F in X, suppose it starts, which starts and ends at our base point, looks something like this. There exist loops which are I, some kind of family of loops HI, labeled by index I in A alpha I. So they belong to some particular space A alpha here. We're finding a number of them, so they're just labeled by indices 1 from 1 to n, such that our loop F is homotopic to their composition. Here is that, okay, you have some loop F, but here, which kind of goes as a vicious in our space X, but the point is you can always consider a bunch of just loops H1, H2, H3, H4 as you want, so that they are contained, each of them is just contained in one of these open sets. So that their composition of this loops Hi is homotopic to our big loop F. And this is what we will prove next time. But are there any questions? This will, this as you can see, this kind of will allow, we'll get some sort of relation between loops in a bigger space with the loops in kind of its subspaces. And particularly this will be used later to kind of calculate a fundamental group in a space by covering in some patches. But if you don't know already, the tutorials were transferred from tomorrow afternoon to Friday morning. And the deadline for submission of the problems is also transferred to Friday morning. But I think probably Patrizia already notified you. If there are no questions, that's it for today.
Thank you.